Hi, good afternoon. My name is Peter Jones. I'm from Senceive, and I am going to give a short talk on wireless remote condition monitoring for dams. Before I move on to the first slide, I'd just like to give my thanks to Kyle, the group chair of the Young Professionals of the British Dam Society, for the opportunity to give this chat. And I hope that whoever is watching will take away a little bit of new knowledge with them. So let's move on. We'll just look at what wireless remote condition monitoring means. We'll look at some of the values and benefits that can be obtained from wireless remote condition monitoring. We'll look at some asset management challenges, solutions and applications, and then finish off with a couple of case studies. So what is wireless remote condition monitoring? Well, it really is as it's written. Wireless, it just means there is no cabling between the sensor and the data hub. Remote, well, we can do it from a distance. We don't need to be there. We don't need to send anybody there. Condition, the status, the performance, or the behavior of something. And in this case, it would be the asset. And monitoring is continually observing and measuring. So what we'll have is a stream of data which we're able to then make informed decisions of the asset. So what are some of the values and benefits of performing wireless remote condition monitoring? Well, first off, and in no particular order of priority, you're going to get near real-time data. So let's say within an hour of taking a measurement, you will know what that measurement is and whether it's produced any change. We can have reliable and repeatable sensor data in all weather conditions. And obviously we know how variable weather conditions are, and with climate change as well, they're going to become more variable in the future. Risk mitigation. This is essentially about safety. Early warning of trend change that could lead to failure mechanism. We need to know if the behavior of the structure is changing. And they are looking, and that's about looking for changes in trend. Remote access. Well, in today's world, we want to avoid costly manual monitoring. We want to avoid sending people out onto the field regularly and reduce the boots on the ground, as they say. Now, that is particularly important in the rail sector, where there's a huge effort to keep boots off the ballast. Finally, ease of installation. Cableless sensors, they're usually plug and play. The mains power-free gateways are easy to set up and just run off solar panels. So there's no need to find main power sources to have these systems up and running very quickly. So in terms of the asset management challenges, what I would say is two things. We want to know the performance of the structure, of the dam, what is normal performance, and secondary, in terms of secondary, in terms of monitoring the dam, when should we commence and how much monitoring should take place. So that really depends on when you start monitoring. So if you look at the sort of lifetime curve of a dam, the deterioration or the decay of the dam over time. So if I highlight this particular curve, when we start off, the dam is brand new, and as the dam ages, obviously its performance will not be so good and will decrease. Now if we start monitoring at point A, we know exactly how the dam is performing when it's brand new. We know how it performs through the 4 seasons. It's going to move, it's going to breathe even during the 4 seasons when it's performing normally. The further along this curve we go before we start monitoring, we will actually never know how much of a decrease from the normal we've actually got to. Because if we don't know what is normal to start with, when we start monitoring, it might actually be at this point that we're monitoring, but we wouldn't know. So the further we go along this deterioration curve, then essentially the amount of monitoring is going to increase, and whether the dam can be saved and remediated becomes less and less likely. So if we were to look at a particular metric to measure for early warning of some change in performance, essentially we could look at the structure itself. So we could look at stability, we could look for cracks, we could monitor strain, or even on an earth dam we can monitor some of the geotechnical properties of the earth itself. We can also look at the surroundings, so we can look at the reservoir water level, we can monitor rainfall and temperature as well, and then we can try and correlate certain movements maybe with changes of season, changes of the water level. Obviously you don't want to confuse the movement of a dam just due to the changes of the water level. It's nothing about failure. So if we were to look at 2 different types of dams, maybe a gravity dam and an earth dam, I would say intuitively maybe we'd be looking to measure rotation or sliding on a gravity dam. Potentially we could look at some sort of wedge or rotational failure of the soil on an earth dam. If we start monitoring very early, we don't have to do excessive monitoring. We can pick on the 1 or 2 priority metrics which should give us the idea, the early warning that performance is falling below the normal. So applications and solutions. So I've split it into essentially four activities. So we're looking at the sensor networks themselves. The sensors need to have batteries and longevity. We need to look at the resolution of the sensors, the reading resolution, and the reporting rate. The sensor network needs a gateway, and it needs a platform, a wireless platform, to be able to communicate the data between sensor and gateway. And the gateway needs to be powered to be able to communicate them back to the cloud server. So in a dam, we really need to be looking at solar power. After we've collected all the data, we need to send it back to the server relatively frequent intervals, maybe every 15 minutes, 30 minutes, even an hour. Usually data backhaul can be through a cellular network, or potentially through a Wi-Fi, signal. So then the data will get to a cloud server, and it will be stored in a cloud server, and then there will be a visualization user interface to the cloud server to be able to interrogate the data. And you may need to look at how to access that data. It can be by computer, it can be by any device, tablet, phone. We need to be able to control the network, make configuration changes through the visualization software and configuration software. We need to be able to interpret the data, do analysis, and you will need to make sure that the system health is continually checked, and alerts can be issued when thresholds have been exceeded. So in terms of the network at the site, we have a few sensors that we provide ourselves, which are essentially niche triaxial tilt sensors, distance sensors, maybe in-place inclinometers, and cameras for actually getting remote access pictures. You don't have to go to the site. These nodes are sensors and nodes essentially combined. There's a lot of other instruments on the market that will measure strain, pressure, stress, displacement, temperature, almost every metric. We will also have some interface nodes to be able to bring those instruments into the wireless system. And finally, you have to think about what platform you would use to have the nodes communicate with the gateways. And essentially, there are two platforms available. One is a lower frequency platform. It's a long range platform, LoRa. And there's a higher frequency platform which runs usually at the sort of same frequency as a Wi-Fi in your house, 2.485 gigahertz. So the mesh network has a much greater bandwidth than the LoRa, which is a single frequency. So you can the amount of data you can send and frequency is much more in excess than the lower frequency. But essentially, the lower frequency means that you can send the data over longer distances. So let's just move on. So it's fine having all these sensors, but we have to understand the importance of data. And it really is the important part of all of this early warning system, is having suitable data. If I was to look at this true value here of a metric, whatever that metric may be, if we could only get a resolution of say 0.25, then we wouldn't be able to determine any trend change until we're really up here. If we were to get a resolution of 0.1, we would be much closer to the true value, and we would be able to detect those trends much earlier. So for instance, we could detect this as a very linear period where the performance is very stable. Once we start to deviate off the true curve, then we will realize that there is a trend change. Now, we can only detect that trend change if the interval of resolution is small enough. So being able to go from the stable to the rapidly changing trend, it's important that the resolution itself of the data allows that, and that includes the repeatability, the scatter, the noise, taking out from the background. So just a couple of case studies where we've put our instruments on dams. This was Burnhope Reservoir in conjunction with some satellite monitoring. We put about 84 tilt sensors on these coping stones right the way across the dam. It was about trying to assess movement of the crest of the dam in relation to movement or the height of the reservoir water. Second case study would be the Alge Reservoir, and that would be here a series of beams interconnected with a tilt sensor on each beam, and that would give a lateral deflection profile if there's any movement of the dam, if there's any tilt happening. And finally, some potential uses for an earthwork dam, very similar to what we do in Network Rail. For the earthworks monitoring, we have tilt sensors on stakes which are embedded into the earth. If there's any slope slippage or any rotational movement starting to happen, then the tilt sensors will pick up that movement. Similarly, we can monitor for the reservoir water level, and we can also look at potentially sliding, as I mentioned previously, as a metric by putting some optical displacement sensors on the back face of the dam and reflecting off something which is in a stable location. And that is the end of the presentation. So thank you very much.